Well, hello there, and welcome back for more Advent of Code. And this is day 25, Snowverload. So I started this thing yesterday, and I don't know actually if I will upload a video of that, because it's basically me trying to, for 2 hours, trying to understand a graph theory algorithm, which is called Stoer-Wagner algorithm. And it's an algorithm to find the minimum cut on a graph, basically. Are there images here? Well, not a very good one. But yeah, the idea for the puzzle itself is that you are given a diagram of components connected with wires. I will put a stopwatch also. And you want to find the 3 wires that you need to cut in order to make this sets of components, this interconnected thing of components, separated, disjoint. This is apparently a well-known graph problem, which is called minimum cut problem. And this is one algorithm that can be used to solve this. And there was another algorithm, which is called the Karcher's algorithm, which was, I think, more interesting because it is like a probabilistic or randomized algorithm. Like, it's not guaranteed to give you the answer right away, or if you have it requires random number generation, and if you have bad luck, you could be running this for a long time. But I don't know, this seems a bit outside of my comfort, too much outside of my comfort. This one is also pretty, I don't know, not convoluted. Once you read about it, you kind of understand what it's doing. But all the Wikipedia article for itself that explains it is based on a paper, and I have the paper open here also. And actually, the paper is more readable than the Wikipedia article, because the Wikipedia article is just referencing things from the paper, and it's not doing a great job at that. But it has this kind of, this is copied verbatim from the paper, and it has this kind of problem of the pseudocode not really being very concrete at all about what it's doing. So you kind of have to interpret these things. And what makes the Wikipedia article worse than the paper is that at least the paper has a concrete example with pictures that you can follow along. And once you follow this along, you kind of understand this, or at least in my case, I kind of understood what the algorithm was doing. And besides that, there is an example implementation in very concise C++ that supposedly implements this algorithm on an adjacency matrix data structure. So you can represent a graph using a matrix with a weight of, if each column and row of the column of the matrix will be a node, like the index of a node, and each cell on it would be the weight that connects these 2 nodes. If there is an edge between those 2 nodes, there would be a positive weight there, and that's what this matrix would represent. In our case, our graph is unweighted, so we would put 1s where there is a wire and 0s where there is no wire. But this algorithm actually uses this matrix and modifies it. Like you can see here, it modifies the matrix that is passed in. And this C++ is very, very concise. It took me, I don't know how much time. Today I was reading it again to understand some of things. pH here, it refers to the phase of the algorithm. So you run many phases, basically n phases, where n is the size of the graph. That is the amount of nodes. And we can see maybe, yeah, here is the minimum cut. So yeah, it's not really what you're doing in this algorithm is basically kind of reducing the graph running one of these contraction phases, you can see that here this node was chosen to be reduced, and it gets like joined with like the S and T nodes are the last nodes basically that are chosen in this algorithm, and the T node, the last one, gets collapsed with the S1, and then you run one of those contraction phases again and again, and you go on and on contracting one by one. So you're basically going to run n contraction phases, or n-1 maybe. So we can maybe check here. Yeah, it starts from 1, so instead of from 0, so you would be running n-1 phases. But this does the modification in place on the matrix. And by the way, it uses matrix, so it always starts from the same node, the first node on the matrix. On the paper, it says that you can start like each of these phases. You could pick an arbitrary node to start with. But yeah, okay. What I was thinking that I wanted to try to do is I would either try to implement this algorithm like on my own, using either an adjacency matrix or a graph. So what the little code that I produce is just a code to convert this input into like the shape of a graph and make it bi-directional, or like non-directed. So you have in the input, you don't have all the nodes listed on the left. Some of them only appear on the right. For example, I don't know, this one, for example, only appears on the right. But it is also a node that is connected to 4 other nodes, or 5, I guess, because it's connected to this one. Yeah, it appears 5 times here. So this code is just reading the input and creating a graph in the shape of a hash map from a node ID into all the nodes that it is connected to, and it goes both directions. So we insert from A to B and then from B to A. Very simple thing. This, I think, we could try to convert into. So what I was thinking is either we convert this into an adjacency matrix, or we keep it this shape or something like this, like keeping the ID, the alphanumeric IDs and things like that, and try to work that, with that and implement this algorithm, like probably based on the paper. I should close this and the C++ reference. I was checking some of the C++ functions to remember what they do. Remember or learn, actually, because I have very little experience in C++. And very old experience, like C++ 11 is too new for me. So yeah, that's one of the possibilities, trying to implement this thing with the little information that is on the Wikipedia article, but mostly from the paper itself. Oh, and by the way, I also have here open the repo where this code is taken from. The actual implementation on the repo is even more concise. You can see like this is like a bit thinner vertically than this, and this is because it's using even like more concise things, like this rep thing is a macro. That is just a macro for a for loop that says from 0 to n do this, and then from 1 to n do this, and so on. And I don't know, things like vi, for example, is just an alias for vector of indices. So this is even more concise. But I think this code is legit. Like this thing probably works. There are some tests even here. So I trust this thing. I think this is code like for some code competitions or something like that. So if you ever need to do a global min cut on a graph, you can use this, and it's for like this kind of like super lead code kind of competitions. I guess for Advent of Code, it can also be useful. But yeah, the second alternative is, instead of trying to implement this algorithm on my own, I was thinking, why not copy the C++ implementation, translate it to Rust, and then try to make it work and see if it actually works. And then maybe once I understand, because I don't really understand everything that goes inside of here, it's so concise that my brain just melts a little bit. I understand, like, I can understand every statement and part of it individually, but what it's doing, like, okay, you're running each of these phases, each of these, like, it's a cubic algorithm, and each of these phases has this nested 2 for loops. That is a quadratic algorithm for each that finds an ST cut to make, and S and T are indices. Yeah, they are basically indices for a single row. So yeah, I start to make a little bit of like not understanding there. So I kind of follow what this is doing, and then it's keeping like the best. This is something that also I didn't really understand yesterday. Here it's calling the min function with the previous best that you have, which is starting at, like, best is just a pair of two things, an int and a vector of ints. So I'm guessing here that we are going to have the minimum cut size. It's going to be the first component of this, and then the rest is going to be well, I'm not sure of that. So in the example on the paper, the best cut, so you do these phases, but each of these phases can find the minimum cut, and in this case it was, I think, on the 5th phase, the second, blah blah. Here in the 5th case phase here, this is the node selected as T, and the connectivity of this is 4, and this is actually the minimum cut. So you find this on the 5th phase, but you have to do all the phases to find the minimum of those. And by the way, cut of the phase is like, okay, is the cut corresponding to that phase? That's something also that I was not understanding yesterday, but now it makes sense. But yeah, I think I will try to go with the second option of trying to like convert this C++ code to Rust, because I trust this code a bit more than I would trust myself trying to implement this algorithm. And we can then fill the code with print statements or something to try to understand what it is actually doing, and maybe like refactor it into something that I personally find more readable. I think one of the main problems with this, like for my head at least, is that it's working with an adjacency matrix as an implementation of the graph, and I'm not really used to doing that. So everything that modifies that matrix, like I have a very hard time following that. Following pictures like this is super easy for me, but this thing of just a square matrix of weights is a bit too abstract. But yeah, that is kind of the idea, I guess. So we have to convert our graph that we have into an adjacency matrix, convert this code into Rust, then feed our graph into this and see what comes out of this. And then I think this is going to give us the minimum cut. I'm not sure also if this best cut that is returned, like the second parameter, it seems to me, but I'm not really sure, because the second parameter is fed with so there is this second nested like matrix here, but this is not a matrix. This is a vector of vectors, but they can be different lengths, and it's like the accumulated cost for. But I'm not really sure. So that is what gets put into the best thing here, and I think I'm making a lot of nonsense here. Before I was explaining what minimum does here. So minimum here, since it's being passed a pair, it's going to keep the pair that has the least cost. Like basically, it's going to compare the first element of the 2, and since this is starting an int max, it's going to keep the minimum basically. And then the second element is going to be this a vector from this 2D vector thing. And I suspect that this will contain all the nodes. So like here, when you make this cut, this single node represents all the nodes, 3, 4, 7, 8. So if you make this min cut here of weight 4, you're going to be cutting this graph into 4 nodes, 3, 4, 7, 8, and the other nodes of the graph. So with that, we would already have the answer for the puzzle that we need, which is, in the puzzle that we need to find the cuts of, cuts of size 3, the 3 wires that you need to cut, and then see the sizes of the 2 disconnected components of the graph and multiply those two sizes together. So this would be, in this case, like 4 times 4, 16, and that would be the answer. So I don't think, like, once we have the cut, I don't expect to then have to implement like a search algorithm to find what are the disjoint components of the graph. But I'm not really sure. So with all of that being said, let's try to program something actually. I'm going to copy this code and just paste it here. And yay, it's another language, and we are going to try to convert it line by line, probably. Before that, should I try to convert this graph into an adjacency matrix? I'm not sure. Yeah, so that's basically the plan. And the sample input here might be even a bit more complicated than I want, because this already has like 15 nodes and the minimum cut of this is 3. So maybe I would also try to add another example, like a simple graph that is just the graph from the paper, like try to emulate this thing and try to see if the algorithm actually finds the same solution from the paper. But, well, I don't know if that will be necessary. So yeah, I think first I would like to convert this graph into an adjacency matrix. So how do we do that? Can we construct the matrix right away? Not so sure about that. Let's see. One thing that we could do, because once I have the graph like this, like creating, yeah, I think I'm just going to keep this graph. Well, but I also need like indices for the nodes. I also need the node indices, yes. Right, and if I have the indices, so I need to have a map from all the nodes names into the indices, basically. And if I need to do that, well, once I do that, it's like, why do I need like I could just have the adjacency matrix right away, I think. But let's see, well, I'm going to extract this into a separate function later, but let's say that I have the graph. Yeah, this code is, well, it's assuming some things from the input, but it's fine. It's fine. Let's have the yeah, the node indices, how are we going to do this? We can, for example, say get the graph, get the keys of the graph. These are unsorted because it's a hash map. I would like to have the same keys and like have consistent ordering. So like if I would be building this while parsing into already like a vector like structure, I would have that ordering like based on the input. But since I parsed everything into a hash map, I would have lost this ordering. So I think I would just try to sort this thing. You can use sorted from itertools, which is a very powerful iterator. And then once I have the keys sorted, I can enumerate them, right? So I'm giving each node an index with this, and then collect this thing into a hash map, right? If I'm not mistaken, if I didn't get problems here. So this is a hash map. Oh no, this is going the other way around. I don't want these. What I want is, well, I want to flip these two things. So I don't know if there is a good way of doing this. So let's just flip and say node index. I'm going to have, no, this actually gives me the index and the node. And I want to have node and index. Why is, oh no, this should be a tuple. Yeah, and now this double reference here, we can have one less, no, one less in direction. So yeah, these are the node indices, great. And then we can build, I think, the adjacency matrix. We can say, let's mute matrix is going to be a vector of vectors of size. We can have the size already, right? Let's n be graph length. Oh, I can put the n here, right? Oops. We're going to start the matrix with all zeros, and it's just going to be a square matrix. And then what we want to do is iterate this graph, basically. So for each node and what this will be the adjacent nodes to this node in the graph. Yeah, I was going to like make this smaller, like abbreviate this, but I realized like abbreviations, like if you over abbreviate things, how you end up with code like this. So let's not over abbreviate. It's not like that code is wrong. It's just like it's super concise. And to me, at least, it's not the easiest to read and understand right away. You need a sort of an explanation of what it's doing. So, okay, let's fill in this adjacency matrix. So let's say let's I would be like the index of the node itself. So node indices for the node. And then for each adjacent, here we can use an abbreviation, in adjacent nodes, we're gonna have the index of that adjacent node. So node indices for this adjacent node. I don't know, there's probably a better way of doing this. We can probably do it while parsing, but let's do it just step by step. So finally we have the two indices, and we're just going to say that the matrix at I and j, so the adjacency between I and j is 1, and the same thing for j and I. So it's a symmetric matrix, this thing. So I think that should be fine. We can maybe print this, but it's not going to be super easy. So, but let's print, like there's a couple of things that I want to see. I want to see the indices. So node indices. And also I want to see this matrix. So let's do println matrix. Next, have some space, and we're going to print the matrix joined by new line. Although this is probably not going to, the join is probably not going to work. Well, let's just do a for loop then. For row in matrix, let's just print line. That's a row in debug mode, and the node is also debug print, and we can run this with a sample. And look at that, there is a matrix of ones and zeros. How beautifully understandable that is, right? You can clearly see the graph. Not really. But well, there are no ones in the diagonal. That's nice. That's nice to know. That means that there is no component that connects to itself. And it kind of looks symmetrical, like there is a reflection along this diagonal for both sides. It kind of looks like it. You can kind of see that. So, okay. I'm kind of trusting that this is the adjacency matrix. So with that being done, let's clean up this. Let's convert the C++ code into Rust and see what happens. So how am I going to do this? Well, let's just kind of do it. This is the return type, so we're going to say function global min cut is going to return pair of int and vector of int. So int in C++ is signed, and I don't think that this needs to be signed, but I would probably want to keep this thing as is. So let's keep the shape and everything that the C++ code does, even like signed and unsigned things, and then we can try to see if this will work also with unsigned, using zeros instead of, or 0 instead of int min and things like that. Like if it works the same for unsigned. I'm not sure if that is the case, so I will keep the signedness of things. So a pair will be just a tuple, because Rust has tuples. Instead of ints, let's use signs, 64-bit signed integers. Why not? and this will be a vector, I think it will be a vector of nodes. So in our case, they should be usize, but let's just keep it as this. By the way, the matrix is going to need, oh, the matrix is, it's already signed. That's awesome. We can just say that this is 62-bit. That's great. That is great. If these are indices, it's not going to be great for us because we're going to need to do some conversions, but I think the conversions are going to be done inside of here. So this takes the matrix, and this is just a vector vec of I64. So these are the weights, and the types goes after the names in Rust. So that will be the signature of the function. The best is going to also be a pair. So let's say let mute best well, this is going to be a vector. It's going to be this thing basically. Probably don't need the type here. Now let's trust the type inference because we are returning this thing in the end. So if we do something wrong, we are going to know. Like Rust is going to tell us. But we start this thing with I64 max and just an empty vector. Great. Then yeah, n is, oh, that is fine. Let n be the math length. Then this very beautifully named co variable that is just going to be, I guess it refers to costs, but I'm not sure. Here basically is defining the size of this and then like creating this with a given size and then initializing each of the elements with a singleton, like a singleton vector, a vector with only that I. So this can be done in a single assignment, I think. But let's keep the shape of the Rust code, of the C++ code, sorry. So let's initialize this as a vector of size n and a vector with what? Just empty vectors, I guess. This is going to be mutable also. And then we are going to go from, yeah, I from 0 to n, so I in 0 to n. And just do this horrible thing, horrible initialization, which we could have done here, but yeah, whatever. Then we're going to go through all the phases from 1, not from 0, to n. So this is the same as saying from ph in 1 to n, right? And ph is only used here, so let's actually call this thing phase. Have a better name for this. Then we are going to have the weights or the w vector, row or whatever, or column. So let's say let w be the mat at 0, but this is moving out of the matrix, which is going to be a problem in Rust. Here we're going to need to clone, I'm pretty sure, but Rust is going to tell us about that we are moving out of the matrix. So in C++, that was making an implicit copy, I think, of the row. And in Rust doesn't want doesn't like to have implicit copies of things, like things being copied just because you assign something. So it makes you do an explicit copy or clone. We still don't have that error here because we have a bunch of other syntactic errors before. But okay. Then, okay, S and T are size T instead of ints. So these are actually, indices. That's a new one. And they are starting at 0. So S and T. So we can say let's mute S and mute T. Start at, actually, why am I being so, like, these two have, okay, they are related, but they are not the same thing. We can just say S and T start at 0. They are going to be U size, but let's let that thing be inferred. Here there's a comment of, this is quadratic, but it can be made logarithmic or like linear times logarithmic with a priority queue. We are of course not going to try to implement that. So let's remove the comment. And we are going to iterate from 0 up to n minus phase, and this it is not being used for anything. So this is the same thing as saying for whatever from 0 to n minus phase, do this, and like we don't care about that name. So yeah, this is the quadratic code in the phase. Sure, and here we are assigning WT to int min, whatever this is doing. So this is i64 and min. Then what are we doing here? Oh, a comma operator, beautiful. So S is the previous T, and then T is the max element from, and this is using C++, not ranges, the iterators. So from the starting of begin, and then, oh yeah, all the range starting of begin, the beginning of W, so all the range of W, the max element in W, minus, okay, this is doing minus, so an iterator minus an iterator is like the difference of two iterators, or the difference of two pointers basically, and that is a number. So we are basically getting the index of the max element. That's what we are getting in here, the max element in W. So I don't know why this is using the comma operator here, like there is no need for that. We can say S equals T, and then do T equals max element. Max element, I think, returns an iterator. I'm pretty sure about that. I have already actually visited this to understand what the algorithm was doing, but yeah, it returns a forward iterate. That's good. So we can subtract it and get a size T, or U size in Rust parlance. So how do we do this? Max elements in Rust would be W, not max, but like iter max. But this would just give you the element itself, not the position of it. And what we actually want is kind of the position. So we can actually say position, position max from iter2s. Does this do what I want to do? Cannot find. Returns the position of the maximum element in the iterator. Yeah. That's what I want. that is what I want. And you don't like this because mismatch type. Oh yeah, there must be a maximum. So let's just unwrap. We're going to think about like what does it mean. Like W should not be. Yeah, it should not be empty. So sure. And then we go from 0 to n, and we just assign W I to whatever the matrix. We add this W with whatever is in the matrix row or column for that. So this is basically the collapsing, the collapsing code, which I am not understanding very well, but I think that this is what this is doing. And then like the W at T gets to be minimum, so it's like I think with this we sort of removed that node, if I understand something about this. So we can write this to say for I in 0 to n, we do this, and we are going to use the same syntax here. This is valid Rust. Great. Then the best gets assigned to the minimum between the best and this pair of things. We can just rewrite this. We can use here CMP min from the standard library, or we can just do as a method call use best and min with a pair that has WG minus this, yeah, that is fine, and then this. Here it's subtracting the matrix at TT, which we know it's 0, right? But I'm not sure, because this is like the adjacency, like a connection to itself. Like this is an element on the diagonal of the matrix, and I think this is always zeros in our case, but I don't know if we assign to this thing at some point. So like if we are modifying, because we are modifying the matrix inside of this code, so I don't know. But okay. Yes, we keep the best here. Then we are inserting new stuff into this co variable. We are expanding the S. So the T got collapsed, and then we expand the S. Like we are collapsing T into S. And yeah, these are indices for the nodes. And we are inserting from the ends. Yeah, look at that. S, we are inserting everything that is in co T. So this in Rust, I think, is the same as saying expand. Do we have expand? No, extend. Yeah, starting at the end, that's not necessary to say. What we extend with everything in co T. I'm not sure here if I will need also to clone or move out of or whatever. But okay. And then we go twice from 0 to n and assign the matrix. Yeah, we increment the weights in S with the weights in T, and then we set the IS to SI. We are making the matrix like symmetrical again, I guess, in this for loop. So okay, let's just rewrite. This is the same twice. So from I in, like the indices go from 0 to n, right? Yeah, I in 0 to n, we do these things. Okay, and now the formatter kicked in. And then finally, mat0 at t is int min, so I64 min. And that should be the rewritten thing. And here we have, yeah, mismatch type, because this was expecting a vector of I64, but we are returning a vector of U sizes, which is this and the Okay, so should I convert this? I think I don't want to change the other stuff, so I'm just going to convert this thing. And yeah, let's just say that let best be just best 0 and best 1 intuiter. I just want to convert everything to I64. Whatever is in here, just I as I64, and collect, and this is, well, this is what we are returning basically. So okay, now we have other problems. We are mutating this matrix. Yes, sure, let's make it, we are passing this by move, so we can mutate it here, no problem. Then here is the problem that I thought we were going to have, which is that we are moving out of this thing. The C++ was doing an implicit copy. I think if we clone, that will be fine, and this thing also needs to be mutable, so fine. And then we're keeping the minimum with this weight and this, and I guess here cannot move out of in. Yeah, we are moving out of this, so again, let's add, I think the C++ code was also doing an implicit copy there, so we will add a clone, which is not great to call minimum like this. We can be more explicit and say, hey, if this weight is less than the best, then keep, assign the best. But let's just do what the C++ was doing. And then here, I guess this is also, yeah, I cannot borrow as immutable. Yeah, we're borrowing here. What do I want to do actually here? Well, we can clone it. Let's just make lots of clone as. Can't you? Wait, I'm not sure about that error. Yeah, this is a mutable borrow because you need to extend. Okay, so this happens first, the access, and then this evaluation happens then. So we need to make this happen before, let's extract this into a variable and say, I don't know, code T. Oh, no, what the hell did I do? Beautiful name. And here, yeah, let's not worry about clippy warnings. So, okay, is this a correct conversion from concise C++ to less concise Rust? I don't know. We'll have to see what this prints, actually, or what this gives us. So let's actually print line in debug mode what this global min cut gives us for our matrix. So I'm expecting to, well, either crash or return a pair with 3 as its first element and then a vector of 4 indices. Let's see. Well, the 3 was correct, but the vector has more things. Oh no, it's not 3. Sorry, I said 3 indices. I was thinking actually about the sample in the example in the paper that has like 4 elements, but here we have many more. We have 3, 6, 9, which I think is one of the cuts. So one of the, yeah, it separates the components into 9 and 6. So it seems to be what we want. So we can now do, that's great, actually, global min cut. So we can actually like, let's min cut size and min cut nodes be this thing, and we can just assert EQ or whatever, how is it called, the thing in ensure, I think it is. Ensure from anyhow, yeah. Let's ensure that the min cut size, min cut size is 3. Expected to cut 3 wires. And yeah, after that, we just have the min cut nodes. So we have to, like, the answer for part 1 is gonna be min cut nodes length times, well, basically n minus min cut nodes length. And let's print this. Print ln of answer 1. And for the sample, it is 54, which is what we want. Oh man. Is this correct for the input too? And it's running, it's taking more time. This is running debug mode, and it's a cubic algorithm, and our size of nodes is 1500. So maybe that's a big thing. Yeah, it's taking some time. So let's run in release mode at the very least. So it's not the fastest algorithm, as we can see. So maybe some optimization is going to be needed. Oh, but we got an answer, and it also ends in 69, which is, I don't know, a coincidence, I guess, with this number here. Let's submit this. Yet, it is. it is the answer. And we didn't really understand what that algorithm was doing, but it did the job. So that's awesome. And usually, I don't know if we are going to have a part 2 for the 25th day, because usually if you have already the 49 stars, part 2 comes for free. But let's see. You climb over weather machines under giant springs and narrowly avoid a pile of pipes as you find a disconnect the 3 wires. So yeah, this is a pile of stuff that we have been collecting from the previous days. It's all joined together in a monstrosity of connected thing. A moment after you disconnect the last wire, the big red reset button module makes a small ding noise. System overload resolved. Power required is now 50 stars. Out of the corner of your eye, you notice goggles and a loose-fitting hard hat peeking at you from behind an ultra crucible. Is this the reindeer from... You think you see a faint glow, but before you can investigate, you hear another small ding. Power required is now 49 stars. Please supply the necessary stars and push the button to restart the system. You have enough stars to push the big red button. Although it hasn't changed, you can still get your puzzle inputs. Yeah, push the big red button. Yay! And it's snowing. You supply all 50 stars and restart global snow production. As you reach the edge of Snow Island, you can already tell from way up here that everyone will have a white Christmas this year after all. Yes, especially in the southern hemisphere, which is, well, it's not too hot today, but we're having days of like 30 degrees or more. So this is a very northern hemisphere centric theme, but whatever, like I'm used to that. You have finished every puzzle in Advent of Code 2023, yay! I hope you have as much fun solving them as I have making them for you. Well, thank you very much, creator of Advent of Code. I don't remember your name, but you are awesome. I'd love to hear about your adventure. You can get in touch with me via contact on my website or through Twitter and Mastodon. Maybe I can learn this guy's name. Yeah, Eric Wassel. Thank you very much for doing Advent of Code, man. It's always a pleasure to do these things. So if you'd like to see more things like this in the future, please consider supporting Advent of Code and sharing with others. Sure, I'm sharing with others through YouTube videos, and maybe someday I will also monetarily support you, but that's not going to be today, sorry. I'm unemployed. But anyway, yeah, this was a very interesting puzzle, and I definitely learned new things doing this. Like, there are algorithms to find minimum cuts on graphs. Things are kind of slow. Also, let's time this thing. Let's build cargo build in release mode, and yeah, time this day 25 with the 25 inputs. So it is taking some seconds. It's taking 8 seconds to run, which is not great. You can definitely try to optimize this. But yeah, converting the C++ code to Rust actually worked. And this is wanting me to do stuff. I don't know why. To index. Yeah, okay, this is used to iterate over here, and we can of course like fix the warnings now that we know the answer. It's taking 8 seconds to do each check, so that's not going to be fun to run again and again, but okay, we can make this thing a bit more rustier. So for example, this initialization here that we are initializing this way, I think we can rewrite this pretty easily and say, hey, this is just 0 to n, and map this number to a vector with that number. Sure, and then we're just going to collect this. And this probably needs now a, well, we can use collect vec from itertools, our friend itertools. This should still be the same. Oh, we should also put this into the answers file. So this thing goes into the answers file as day 25. This is our answer, and we still have the same answer. Great. Now here we are assigning W, everything in WI, we are adding matrix at TI. So actually, like, I think this is the best way of doing this. If we do like for each, it doesn't make sense. Let's actually cargo Clippy. Let's read the Clippy warning here. Yeah, iter-mute enumerate, that like that is not better, I think, than this for this kind of like matrix heavy code. I don't think it's much easier. Like this would be the same as saying W iter-mute, and we're just going to have an enumerate. We also need to enumerate this just to say I and WI, right? And you are basically assigning WI to this. I think this would be the same thing as before, but like it's not more readable at all. So I think we can leave that cargo, that Clippy warning, or maybe suppress it. Because yeah, I don't think that this is better than this. This is actually quite shorter and more readable, I think. Yeah. WI. I guess we can also, since we are adding everything into W, we could maybe say like W is W zipped with, is there a, well, there's a zip with, right? Zip. You can zip with, I guess, matrix T and say, but we have to like map and collect this thing. So it's, again, it's not better. But let's leave this Clippy warning there. I think I'm going to just commit this as it is now, and well, this is going to take 8 seconds to check, but let's assume it is correct. Yeah, let's say add day 25 solution. And also this thing definitely warrants a comment. This comes from this, so computes the minimum cuts of a graph given minimum cut of graph using the Stoer-Wagner algorithm. The graph is given as an adjacent. How is this thing spelled? Adjacency. Yeah, matrix. I don't know how to spell. And we can leave a reference to the beautiful Wikipedia article, and maybe to the paper. Like the paper is beautiful. It's in a emax.ru site, in a Russian site called emax with double x. I am afraid to visit the site and discover if it's a porn site or something like that. So I don't think I won't do that on this video because I don't want to edit something out. But yeah, we can leave a link to Wikipedia for this. So let's actually amend this into the previous commit. Okay. So this code is very unrusty, I would say. One thing that I would like to try out is to see, since we are given this adjacency matrix with weights, the weights could be negative, I guess, but then the return, like the return of this, when we can print actually the min cut nodes. So print line min cut nodes is gonna be this min cut nodes as debug print, and we can run this with a sample. So these things are they are the indices of the nodes in the original graph. So let's go to check the advent calendar, and look at that. The snow island is providing snow. That's awesome. That's really great. Beautiful. So what did I want to see here? Yeah, the components here should be these. So we should print this and the indices. Node indices. So okay, let's check. Like index 5 is LHK, which is here, yes. And index 2, I'm not going to check everything, but just a few of these. Index 2 is, where is the index 2? First, and each, yeah, it's here. So I guess, yeah, this indices are correct. Otherwise, we wouldn't have had the correct answer. But definitely, then the return type of this should not be i64. It should be indices on that adjacency, like the nodes themselves. So this should be usize for sure. And so then I think we won't need to do the conversion here. We can just return best like this. And yeah, nothing complains inside of here, so that's awesome. Can we keep going? So I guess all of the like int min and int max is used because well, we are computing the weights. I guess the weights can be signed integers, like why not? They are different than the indices themselves, and we can like separate what is like weights and what are nodes, basically. So that is fine, I think. There are some extra clones and copies that... Oh, I also want to see if this is necessary. I think it shouldn't be. If we run this now with... Well, we can run check all, basically. Oh! Expected to cut 3 wires, so was that actually? Or no? What's the change to... What? Okay, so math.tt is actually important. It was not just for self-connecting components. So that's interesting, the way that we are modifying the matrix. So I don't think I will have a very good time like trying to follow what's happening for the sample. I would have to recreate, like, to understand this algorithm. But I'm happy that it works actually, and I don't think I clippy needless range loop. Yeah, needless, but I mean it's not needless. Come on, it's better to just do this. Although we could say something like W. There's not a zip, but intermute zip with math T, and here we'll have WI and something like this, and then do like WI is plus equals math I, but I don't think... Yeah, and you're moving this so we can iterate. Like, would this be better? I don't think so. Like, I don't think that this is... Now, this is definitely not better than just doing this, so... Yeah, last time that I'm trying to change that. I will change the whole algorithm to not work with an adjacency matrix before doing this kind of thing. So, yeah, this is... Okay, reference to the algorithm itself, but I would also like to reference this nice implementation, which is what we copied. So I will just link the GitHub thing. And yeah, we can... Do we have this thing in different branches? Main, there are no tags, this is just main. So yeah, let's grab the actual commit. If you do, if you press the Y key, it gives you like a more permanent link. It's not small, but it's fine. This implementation is just a translation of this CPP, C++ code. Okay, so yeah, let's leave a reference to the original. And do I care about understanding this? I'm not sure if I do. Global main cuts. Yeah, maybe the first part we can try to make it better somehow. So the first thing that I would do is to try to extract this thing. And look at that, it's returning, okay, n, and why does it need the n? Oh, because it's, yeah, let's call this thing parse graph. And this is just going to return the adjacency matrix of the graph. No, not necessary to return the size. So just return the matrix here. Whoops. Yeah. And the n. Yeah, we are ensuring this, but do we even care about it being 3? Expected the minimum cut to be 3 wires. Got, and can we print this here? Min cut size. Yeah. To be, I want this to I like this to be a single line, but whatever. Is there an ensure EQ or something? Just ensure. Anyhow, yeah, it's just ensure. Do we actually care about doing this ensure? Not really, right? Minimum can be, well, cats are free, goats. Why don't you want this to be a single line? Come on. Like, it really fits on the line length, but the heuristics of the formatter is something that sometimes drive me a bit crazy. But yeah, this doesn't want, okay, whatever. Not length. Okay, we have extracted the parsing thing. So now it's not too bad, I guess. Oh, we have, here we lost, since we moved the matrix into here. Yeah, I guess we can extract this into a variable and call this thing graph size instead of just n. We get the global min cuts, sure. And let's call it cut size, like we don't need to, and cut nodes. We know that the cut is the global min cut, and even with that, the formatter refuses to have this. Maybe this is a heuristic for like macros or something, or for print macros, that if you have some things to, oh, but I could just inline this here, I'm an idiot. So now, well, it's a bit better. It's a bit better, whatever. Okay, this should still pass all the checks. I guess it will. And yeah, that's great. And what I was wondering is, here we are parsing the graph and then converting that graph into an adjacency matrix. But do we need to do so? Probably not, I think. And the sorted, I was using the sorted here to maybe like have stable indices, but it shouldn't be needed for the correctness of the algorithm. So I guess if we don't sort this, well, it works the same for the sample, and I hope that for the real input it does so too. Man, this algorithm takes some time, but okay, we don't need to sort. That's great. Let's add this. I would like to try out to just parse directly into either into the adjacency matrix or into something that is a bit more similar to what we need to do. So instead of the graph being this, can we have the graph be already like a vector of vectors of USI, so like an adjacency list, basically, using indices already. I'm not sure if this will work, but let's try out. We will need to, once we have a node, we need to have like the index for that node, basically. Right? I think so. So let's also have the node indices, because we need to have some mapping between a name and an index. So yeah, let's mute node indices, new hash map, and when we have a node, we can trust this. I think this subslicing. We could also like do split once by colon space, and we would have like the name of the node and the name of the rest, but we can just trust that the input has that shape and yeah, not worry about that. So yeah, sure, we have this node A. What would be the index of node A? Well, this would be node indices. Give me the entry for node A, or insert a new one, and the new one will be just node indices. Like, what will be the new index? Well, node index length, right? I think so. Oh, but if we have a new one, it also means that we will need to grow the graph itself. We can rename this node A, basically, or shadow this to the index, right? So if we have an index, we cannot just access this graph for this index, because we are going to screw up. But if we do that, will things get better? I'm not really sure. Can we just build an adjacency matrix right away? I'm not sure if this refactor does make sense. So if we needed to extend extend this thing, we will also need to extend the graph. Otherwise, we're just going to screw things up, I think. So node A, or insert with, and if we do the or insert with, will this work? Yeah, we're going to insert this, but we also need to do graph grow the graph itself, I think. So now this is a valid index on the graph. Okay, let's see, but we are going to need to do a very similar thing for the node B, which I think is kind of ugly. Let's try it. We're going to have to do also like node B is gonna be basically the same thing. And then finally, once you have node A and node B, we can do graph node A push node B and vice versa. And this, I guess, are references. We can dereference this thing. Yeah, and with that, the node indices we don't care about. We already have those built. And then node and adjacency node in graph. This is actually, yeah, this is actually the graph iter enumerates. Well, we can do into iter and consume it here. Adjacent nodes, sure. We don't need to access node indices here. We just have node and adjacent nodes. And instead of I, we would just use node. And instead of J, we just use adjacent node. Yeah, and here we are into iter, so this thing is going to be a vector that has been moved, so we can use even into iter inside of this. Does this still check? No, your problem here is that you cannot borrow node indices as immutable because it's also yeah, we are returning this length here, which is a bit annoying. We are pushing this into the vec, into the pushing this into the graph here. So I guess we can also say graph length, like the previous length of the graph is the index for, like, the new index if we needed to create a new index, and same thing in here. But you don't like this now because mismatched type. What? What's mismatched type? What did I cargo build? Why are you expecting? this for node B? Node indices is we're doing or insert with. What's going, like, why is it a map from stir to, oh, because this, I was returning unit there. Okay. If we run this, well, it passes for the sample, and will it also pass for the inputs? Yes, it does. Okay. But I don't know if this is actually much better than what we had before. We have this kind of ugly access to like the creation of the new node is a bit ugly. Maybe we can extract this into a lambda or something. But let's see the difference, the diff. It's like, it's not even shorter than what we had before. Yeah, I don't think that this is a great, like before it was much simpler just to build the graph, and then we were just converting that graph into an adjacency matrix, like more in a simpler way, I guess. Yeah, I think I would leave this as it was before. I think we don't need to yeah, we don't need to like optimize or like this was not a simplification. So let's, yeah, this actually is better. Let's increase the font size again. Oof, maybe a bit too much. We can even like split this into two, like parse graph would be just this thing, and then this would be the thing that makes the adjacency matrix for that graph. If we wanted to, you know, to like make more sense, I guess. Global min cut, blah blah blah. I'm not used to also passing things like by move, like what I'm doing here. But there is no harm in doing this. Like instead of receiving this by move and mutating this, we could receive a reference here and then make an explicit copy inside. But why do that if we know that we are only calling that once and we can just move the thing into there? So yeah, maybe we can, I think I would like to see how separating that looks like if we extract this thing into like a function that is just we can say create adjacency matrix for a given graph. Yes, and we'll just return that. And actually here we could say return the graph, and we do things more like step by step, and have the graph and then the matrix. Create adjacency matrix for this graph. And in here we don't need to take this by move. we can just take this as a reference, and if we do that, then we don't need to do this like graph size in here. We can just do graph length in here, I think, and we pass this by reference. And your problem is that this thing is no longer returning that. It should return one of these instead, a graph. This is taking the input as string. Let's take it as string slice. Yeah, thank you. Oh man, the Rust compiler is so nice. Like, it really guides all those fixes. Should still pass, it seems like. So okay, now each thing is doing less work. Like parsing a graph is doing like very little thing. This returns a bidirectional graph. Well, no need to say that. Like, it's pretty explicit here. Like, then this creates an adjacency matrix for a given graph. That's great. Can we simplify some of this, maybe? Well, n is only used there. We can just inline this thing. No need to optimize that. This I don't think that we will need to declare. And about these, we are getting the keys, enumerating them, this kind of thing, and I would like to like just flip them. Map and collect. Keys and if we are we here, maybe we can do the zip 0 onwards trick. So now we will have the keys like in the right order. Yeah, look at that. What a trick. That's great, and this should still pass. That's awesome. And then we just initialize the matrix and set the things. So yeah, this makes more sense to me. And that seems to be great. Create the graph from the input, we create the matrix from the graph, then find the global min cut, and that's it. That is then the answer. We can remove unnecessary superfluous new lines there. And we only have one clippy warning left, which I would like to maybe needless range loop. Can I turn off the warning for this function? Yeah. Let's do this. Yeah, no comment needed. Like, I think for some things it's better. Like, also these can probably be changed into some other way. But I think it's more readable to do it this way. This is kind of the same as assigning mat t to mat s I feel like. Oh, no, not assigning, because we have to increase. Sure. Okay. Okay. Fine. So we didn't do a great job of understanding what this thing is doing, but it works, and that's the magic of software. Sometimes you can abstract things away and say treat it like a black box, and be happy about that. And we were good citizens, leaving references to the originals. So let's not pretend that we invented these things. So what did we did? What did we do actually now? Just just some minor refactors. So day 25 minor refactors. Okay, and I think that will be it for this video and for this Advent of Code of 2023. I'm very glad to have finished this not so long after the Christmas. I probably do still have some things to try out, especially like this thing, this problem that is now taking 8 seconds to run. I would probably like to try to optimize this somehow, although if I cannot understand really what it's doing, well, now it's running faster. I don't know why. Like, what of the things that I changed actually improved things? Maybe, I don't know why. Maybe now that it's not sorting, like the inputs is finding the minimum cut faster or something. Would that make sense? I don't know. Here, when we are, like, if we do this sorted, does this change the runtime? No, it's actually faster now. So maybe this is just noise in the measurement. But this now seems to be a bit faster actually. But anyway, it does look like this would probably improve. Yeah, now it's slower. So sorting the input keys actually makes the things faster. But this is just changing the order of the nodes in the adjacency matrix, and maybe we, when we sort these things, we are getting luckier in the algorithm. But it's not great. Now here we can probably save some of these of this cloning, although this is not in the hot path. Like, the hot path is this thing. This unwrap is unnecessary, or I would prefer to not have unwraps like this. But yeah, well, I will probably nitpick and continue like refactoring this off video, because this is already a pretty long one, as is being usual for the last videos. But yeah, let's revisit one last thing, which is on the README at the beginning of everything. How do I go? Control home? Yeah. The goals for this Advent of Code, well, having fun and learning things. I have definitely done so. Definitely learned a lot of things, and well, also had a lot of fun doing this. So that, I would say, has been achieved. Fast execution time, well, with this last solution that is taking like 6 or 7 seconds to run, we are not getting less than 1 second for this whole set of puzzles, which is a pity. Optimizing this, I have no idea how to do. Well, the solution said that this could be changed to be linear plus a logarithm thing using a priority queue, but I'm not sure how to, well, I will have to understand the algorithm much better than I do now to properly optimize that. But okay, let's say that we almost achieved this except for the last puzzle. Proper error propagation, this is something that I generally have done. But I haven't really been paying attention to avoiding crashes due to bad or unexpected inputs. So this is something that I probably revisit and try to use what I said here in the README, use adversarial inputs to try to crash the solutions that we have and try to like harden them and, you know, make them propagate the errors up if anything goes wrong instead of just crash. Because yeah, part of the fun for me is like trying to you know, sort of proper engineering or proper good practices on this, on not just coming to a solution, but having code that is robust and efficient. Not so much like correct, like overgeneralize and have a correct solution for any possible input. That is not part of the goal, but not having things crash when having bad inputs is something that I would like to try out. So maybe that will be for the next video. But for now, I'm happy that we got a solution for day 25. And if you have been, I'm happy that you have been watching so far in this video, and I hope you had some fun as well as I did. And see you later. Goodbye.